Today's topic is simple harmonic motion. Also known as SHM in short. Now let's take a particle which goes up, then comes back, then goes up, and keeps on doing like this. This we call as oscillations. Okay. Now there are certain terms associated with these oscillations. One is called period. What is a period? Let us say this particle starts from here, goes to the extreme, comes back, and goes to mean position again, then comes back to mean position again. The time taken for it to cover the whole journey is called a period. And this period can be anything. This can be measured in terms of frequency also. Frequency is inverse of time period. Time period is a time taken to complete a cycle. Okay. So we have time period, and inverse of time period is frequency. Frequency means number of cycles per second executed. Now there is another term called displacement. We have seen earlier also, there is a particle P here, and if it moves to another position P2, the straight line distance between the two is called the displacement. Similarly, in an oscillating particle, let us say a particle starts from here at t is equal to 0, and it reaches here at any time t1, then this distance covered is called displacement. So displacement is nothing but distance from mean position. It need not be from mean position, but for sake of simplicity, we assume we take it from mean position. I mean, you can have displacement from this point to this point also, or from this point to this point also, any place. Now there is another term called amplitude. This is a special term, special case of displacement, wherein displacement, this is maximum displacement from mean position. Mean position means we also call it as an equilibrium position. Let us say there's a particle here, started from here, goes up and up and up and comes back. Now, it started from here and went to a maximum displacement of this. This we call as amplitude of the oscillating particle. Similarly, it will come to the mean position and overshoot, go back to the another extreme position, and come back again to the mean position. So you can take amplitude as this one, or this one, both will be same because it is symmetric towards equilibrium position. Okay. Now, this is as far as an oscillatory motion is concerned. Now, an oscillatory motion becomes a special case of simple harmonic motion for the following reason. If it fulfills certain criteria. And what are those criteria? Criteria number one is that it should have a fixed period. Or periodicity. Period we have already talked here. Second is displacement should be a sinusoidal function. A sinusoidal function is like it could as well be both are sinusoidal. The only difference is that there is a phase lag between these two. Otherwise, both functions are same. Here A is the displacement, omega is the angular velocity, and delta is the phase difference. Okay. The third criteria is that acceleration at any point should be proportional to displacement. What does it mean? What it means is, let us say a particle started from here at t is equal to 0. At t is equal to 1, at t1, it reaches here. The displacement is this. Then the acceleration on this particle will be proportional to how far it is from the equilibrium position, right? Now let's see some treatment of harmonic period, SHM, simple harmonic motion, certain formulas, certain treatments. We've already seen by this function force, which is mass into acceleration. So acceleration is proportional to displacement. This is first criteria. Second criteria, we have already seen this sinusoidal function. Okay. So if we say our x at any point t is equal to if we double differentiate, what we will get? D square x by dt square. This is our nothing but xt initial. So initial x, this was our initial x. So this will get x. Okay. Or force is equal to mass into acceleration is equal to minus kx, implies k is equal to ma. omega square. This is one relationship. That if we express our force in terms of kx, where k is the proportionality of constant, then this proportionality of constant is equal to mass times omega square. Okay, or omega is equal to k by m under the root. Now we also, what is time period? Time period is the time taken to cover 2 pi radians. Okay, with the omega velocity. This is nothing but omega. We substitute from here. So this is our time period. This is another relationship. We can also define T as time period as small displacement and the acceleration caused. Is equal to 2 pi. If our displacement is x and our acceleration is force divided by mass, then this becomes force. We have already seen was kx, mass moves up. So what we are left with is T is equal to 2 pi m by k. The same relationship we talked earlier. Okay. Now, this was for when the body was executing a linear motion. What if the body is executing a circular motion? Then what we get is T is equal to m gets replaced by moment of inertia, k remains k. This is for rotating bodies. Talking about rotational bodies, let's talk about a rotational pendulum. What is a rotational pendulum? Rotational pendulum, nothing but we take a disc, suspend it from its center by a torsional wire and give it a slight twist. Now what happens is we give a slight twist and release it. Then this body keeps rotating. It will go like this, then it will go like this. So it will keep on going like this in a simple harmonic motion. Now in such case, torque is equal to minus k theta, taking the above analogy of this one. Now instead of x, we take theta. Instead of x, we take theta. Okay. And we have already seen torque is equal to I alpha Here I is the moment of inertia. This moment of inertia will be about this axis, this disk rotating about this axis, moment of inertia, and this is angular acceleration. Okay, so alpha becomes a theta by I is equal to minus omega square theta, and omega becomes a by A under the root, or T becomes 2 pi I by K. This is in case of a rotating body or a torsional pendulum. Now let's talk about a simple pendulum. We all know what a simple pendulum is. We have a bob in which when we pull it to one side and release it, it goes in a circular path like this. Now let us suppose this is theta angle. Then what are the forces acting on this pendulum system? One is the mass of the body, another is the tension. Now if we resolve this mass in two components, which is one is in line with T and another is perpendicular to T. This is again theta. So this force will become mg cos theta, wherein this will become mg sin theta. Now this tension will get balanced by this mg cos theta, and we will be left with only this force, which is acting on the bob, which is responsible for making it go in a circular path. And this we call as restoring force. Okay. Now, assuming that the length of the pendulum is this, is L, then our restoring force is F, is mg sin theta. If we express our force in terms of constant times displacement, this is equal to mg sin and sin theta is what? If suppose this was our displacement, we moved our bob from here to here, the displacement is this much, x. So sin theta will be perpendicular upon hypotenuse, which will be x by L, right? So time period can be expressed as 2 pi. We have already seen earlier. This is our M, and this is our K from here. We cancel out K. So from here, what we get, K is equal to mg by L. That is what we have done, mg by L. So time period becomes this is the time period of a simple pendulum, right? Now let's calculate the total energy in a simple harmonic motion. Now we know force, a particle is being acted by force, which can be expressed by minus kx, or if we perform small work, this will be f dx. And if we integrate the total work, it will be this much, which is equal to w, which is equal to kx dx integral from x1 to x2. This becomes kx square by 2. Okay. So this work done, where does it go? This goes in raising the potential energy of a particle. This is the difference between the potential energy okay, or we substitute K becomes M this is the total change in energy. Okay. Now let's calculate this energy for a sinusoidal wave. We know a sinusoidal wave is written like this. Then dx by dt, which is the velocity, is given as omega a, right? So potential energy is ux equal to this directly comes from this formula, wherein this term is this term and x our x is this is our x. So taking square it becomes this. Similarly, let us calculate the kinetic energy. Kinetic energy we know is equal to half mv square, right? This is equal to half m dx by dt or m. We have already calculated dx by dt earlier as this formula. This becomes it becomes 1 by 2 omega square a square cos square omega t plus delta. We have seen that our potential energy was equal to m omega square a square sin square omega t plus delta, and kinetic energy was m omega square a square now if we the total energy will be potential plus kinetic energy, which will be this is from here and this is from here. So this becomes total energy during SHM is equal to so much. Another topic we study is damped oscillation. You might have noticed when you are riding a bike or a car, and if you are going on a bumpy road, your vehicle goes up and down, but doesn't keep on doing this. It goes up and it makes a few cycles, and then the vibration stops. Why is it so? It is because your oscillations are damped. Imagine if you got a bump and you kept on going like this, you will be miserable. So what is done is, in a shocker system or a suspension system, you have a mechanism which dampens the oscillations. Now, how does it happen? Let's see. Again, we take force acting on a particle and there is no damping. And if we have a damping behavior, this is damping constant, and a term which is velocity of the particle, velocity of the body. Now, this we do some differential calculus. This is acceleration. So mass into acceleration becomes force. This is equal to minus kx minus bv. And if we do the calculus, what we'll get is x at any time t will be equal to a naught e to the power minus bt by 2m into sin omega dash t plus delta, where omega dash is equal to k by m minus b by 2m, this one. So our xt, and this also can be expressed as w naught minus this is square. And where does this omega 0, omega naught comes in terms of km? We have already seen earlier. This was our omega. Omega is equal to root of k by m. Omega is root of k by m. Okay. Now for small b, when the damping is small, then what you get is this is our formula which comes out. And if you plot it, how does it look like? Since now we see you start with any initial amplitude, it keeps decaying as a function of t. So we start with our a this much. In the next cycle, it becomes less. In the next cycle, it becomes even more less. Keeps becoming lesser and lesser. This is our damped oscillation. Okay. Now we talk another topic, which is forced oscillation and resonance. What is forced oscillation? Forced oscillation is that an oscillation doesn't keep happening on its own. We keep adding force to it. And how is it? Same old equation, minus kx, where everything was happening on its own, minus bv. This was our dampening. Now, to this, what we add is we add an external force factor. This is totally external force. Now, what does it do? Let's see. We can again express our x as another phase difference. Now, what happens in this case is that this process goes under a very complicated process, and after a while, it settles down and it starts oscillating with omega frequency, which is of the applied force. When this is our applied force, this is our applied force, and this is the omega of the applied force frequency. And after a while, the body starts oscillating with this frequency. And we call this as, we have already seen this. So amplitude of this particular equation turns out to be F0 is this force. This is the mass of the body. Omega naught is this value. And omega, this omega is this omega. Okay. Now this will be maximum when omega is equal to omega naught. Now, what is this omega naught? If this omega naught is if we define a term omega naught, omega dash, which is equal to this, then what happens is this vanishes. So what you get is A will be simply now if dampening were ideally zero, meaning if suppose this term was zero, then what would happen? Whole denominator would be zero. And what will happen to amplitude? This will become infinity. This is a condition of resonance. And this practically is a very dangerous condition. Because the body may start vibrating with a natural frequency, which can disintegrate the body altogether. Now let us see what happens if a particle is subjected to two simple harmonic motions. Let us say there is a body which is acted upon by one SHM, which is SHM1, and second let's say SHM2. Now if we add them together, what happens is first SHM plus second SHM. Now if we open up these functions, what we get is sin omega t plus cos omega t plus sin delta. And if we arrange it, this becomes this is equal to C now we assume we take a term C, which is nothing but this thing, and we define a term D, which is nothing but this much. So this expression becomes now right. Now since C by C square plus D square whole square plus D by is equal to 1. These two terms individually can represent sine as cos functions, because then if suppose this is sine theta, then we can say sine square theta plus cos square theta is equal to 1. Okay, if that is the case, then our amplitude becomes cos phi sine omega t plus sine phi cos omega t is equal to sine omega t plus phi. Amplitude is equal to A is equal to C square plus D square is equal to A1 square A1 plus into cos delta square plus A2 sin delta whole square under the root is become equal to A1 square plus A2 square plus 2 if this term is under the root. Both these terms are under the root. Now, does it ring a bell? This formula? This formula we studied in vectors. And what did we study there? If you add vector A1 and A2, A1, A2, which is separated by angle delta, then resultant A is equal to A1 square plus A2 square plus 2 A1, A2 cos delta, which is the same formula as this. So what does it mean? It means if you have two simple harmonic motions, 1 and 2, as we started with, one simple harmonic motion, second simple harmonic motion, and the only difference is that their phase angle is different. There is a difference of delta as the phase angle. So if we consider this as vector A1, and if we consider this as vector A2, we can happily add them together, like we did what we did in vectors. Yeah. So we can say that SHMs can be added like vectors. Okay.